So hello everybody and welcome to this session that was given on Saturday the 26th of April, which was about deep neural networks and convolutional neural networks, where we basically will have a little exploration of this new field that we call today deep learning, where we'll talk a bit into neural networks, what neural networks are and what this is all about and how you can use this, for instance, to classify images. Something like that. So, what is a neural network? So, neural networks are basically mechanisms that were inspired by the brain initially. Here we see a real neuron. Just as a comparison, a real neuron is way more complex than what we have today in neural networks. This is, as I said, just an inspiration. But you have basically these kind of gating potentials. So basically, there are kind of currents which connect each neuron to the other with these action terminals, and which basically gate this, which kind of encodes data inside the brain. But this is very far and way more sophisticated, of course, these neurons than the actual neurons that we have in a neural network, in a computer, as we call it. Yeah. So what does it look like in the computer? So we call this the artificial neuron, and the artificial neuron, basically, it's very simple to understand, and you see that there is really a different level of sophistication, so that this is way more simple than what we have in nature. So we have basically here different inputs. These different inputs are weighted, and then they sum together and go into this node here. And in this node, basically, we have an action potential which gives us the output of the neuron. Okay, and the action potential is nothing else than a function which is applied on the sums of the inputs. So what does this look like in mathematical speak? So it's very simple, described here with this formula. So we have I inputs, so we have here in this case 3, but this can be of course way more. Okay. And we sum up these inputs, we multiply each input with its corresponding weight. So this is here xi omega I, okay, like this. And we have then basically, once the sum has been calculated, we apply a function g, which we call the action potential, on this sum here. And this is then the output of the neuron. It's as easy as that. Okay, this is one neuron, and of course we build neural networks. So neural networks, of course, they consist of more than one neuron. So what does this look like? So we have then what we call here the artificial brain, if you want to, or deep learning. So the story is basically you have several inputs, okay. On these inputs you have basically these inputs basically go into these neurons. So these are the neurons, and then basically you sum up here all the inputs with the weights. So each edge here in this graph corresponds to a weight given from some kind of input, which is then propagated as an output to the next neuron. Okay, and on each edge, basically, you have a weight how from one node, basically, you come to the next. And don't forget that in each node, basically, you have this action potential, which is acting on this sum of the inputs, in order to calculate the output to the other neurons that it's propagating to the other neurons in the next layer. Okay, why is this called deep learning? So deep learning, basically, the more layers this network has. So this is here 1 layer, 2 layers, 3 layers, if you want to, 4 layers, and we have these hidden layers. And basically, from more than 2 hidden layers, we can speak about deep learning, because then this is called a deep neural network, as it has so many layers. This is the whole story behind it, okay? And as you can see, this is very simple, because you just remember this formula, and you have basically for each node you have basically 1, 2, 3, here 4 inputs from the 4 nodes coming in front, which are summed up, weighted of course by each edge, then G acts on it, and the result is basically propagated to the next layer. Okay, it's as easy as that. Okay, and what can you do with this? Well, you can then basically train this so that you can say, okay, you adapt the weights so that for given inputs you get the right output. Yeah, and this in this case is a typical classification example. So let's say as an input image I show it cats and dogs, and I show it 10,000 images of cats, and I show it 10,000 images of dogs. Then at the end I can adapt the weights so that it automatically knows, okay, this is an image of a cat or this is an image of a dog, and get the right output accordingly. Okay, of course all of this has to be trained, so the weights have to be adjusted accordingly so that you always get kind of the right output. But we will talk about this in this talk. So as I just said, you can have different inputs. In this case, basically each pixel could correspond to one input node, which propagates the value of these pixel values basically to this next neuron here, where you then have the sum of these inputs, which are then converted using the action potential, using this G function, to a corresponding output. Okay, so far so good. We already got this example. This is a typical classification example. Of course, you can do other things with neural networks. We will show at least one other use case in here. But let's first ask us, what is this action potential? Yeah, so this action potential can be very simple sometimes. So as you see, for instance, we have this here, where we just take basically the maximum between 0 and z. So basically it's just a right line of z. So the more input you get, the more output you get directly from using this function. Okay, then you can use the hyperbolic tangent. You can use the logistic function. I'm sorry, this here should be z and z in this case, and not x. I'm sorry for this spelling mistake here, don't worry. This is the formula for the hyperbolic tangent. So basically we should have here the inputs, they come in as z, and you basically can use the hyperbolic tangent to propagate them to the outputs. Further, we have the logistic function here that we can use. Again, many more functions exist, and it's basically just how basically the summed up inputs are transferred to the outputs. What you want to do is basically, why you use these functions is also that they are very easy to derive, so that you can easily backpropagate your story. So because you need then kind of the derivative in order to adjust your weights during the training phase, but we will come to that. Okay, so how do we adjust the weight? So basically one easy way to do this is using an algorithm which is called the gradient descent algorithm, and this is implemented as something which is called backpropagation. Yeah? So backpropagation is kind of you train from forward to backward, but you backpropagate the errors by adapting the weights from back to forward, and this is called backpropagation, but we will talk about this here. Okay, so how do you do this? So you need again a loss function, so you need some kind of distance between the outputs and the desired outputs, and then you want to minimize this distance. And how do you minimize this distance? Well, in adapting the weights on each of the neurons, so that you basically get that the outputs become the desired outputs, and then hopefully this distance is minimal, something like this. Okay, how can you do this? So the gradient, what does the gradient basically do? If for instance we would have something like just only two weights, so let's imagine we have a field like this, and this is basically the error that we get for these two weights, which we call here for simplicity x and y. And then this is kind of the field of the errors, and we want to minimize the error. Let's say it like this. Well, if you take the gradient, so if you take the derivative, you can see it kind of here. If you take this this x minus x plus h, yeah, and this y minus y plus h, and this h you put it close to 0, then you have what is called the gradient. So you derive basically in the 2 dimensions that you have given here. Then you get a vector out, and this vector, by definition of the derivative points, you can imagine this if you make one step forward, and you subtract this as by the definition of a derivative. You can see that basically you get the steepest ascent direction. Yeah, so you go the direction into the highest ascent, but it's at the same time, of course, if you inverse this, so if you just of the result, if you take it negative, you get the steepest descent direction, and this is what we want. So we get basically in the point the direction where we go the steepest way down from our point into the next valley. Okay. And we can do this in an iterative way, so we can say, okay, we walk a bit in this direction, then we take another derivative, we get a new direction, and this way we walk kind of downhill until we get to a normally local minimum. So it's not really effective for a global minimum, but there are several ways to overcome this, but in general this is the algorithm that is used in order to minimize such problems. Okay, so what does this look like? So we have our loss function L, we have our weights in the neural network, and basically we can say, okay, we generate, this is the sign for the gradient, and as you can see, the gradient is nothing else than a vector where I derive this loss function by each weight that I have in my neural network. Okay. And then I update this, so then I get basically better weights if I take in the next step. So the new weights are the old weights, so the vector of the old weights minus, because this here is the ascent direction, as we heard, the biggest ascent direction, in order to minimize this function L. So we actually don't minimize, but we go up. But as we take here the minus, we go downhill, so we take here the steepest descent direction, as it's called, also, and we have here basically a learning rate. So this is basically how far we go into this direction that we have calculated by calculating all these derivatives, and we subtract this basically with this learning rate from the previous weights, and we get new weights out that are supposed to be better than the ones before. Okay, so as we take the steepest descent direction, we can assume that they are better if, of course, this gamma is not too far. Yeah, so just to imagine this, so basically if I'm here and I calculate, okay, the steepest descent, of course, then goes in this 2-dimensional valley here in this direction, but if this gamma is too big, then I go too far, and then I might end up somewhere higher than I've actually been, because my learning rate was too big. So also the learning rate is a big question, how to estimate this. This is called the line search problem. We will not go into this in this talk, but just to keep that in mind. Okay. And from that, of course, this whole story, of course, one could do this like this. So we could take all the weights and calculate this gradient, and this is kind of cumbersome, but in practice this is way more easier, because we can do something which is called back propagation, and back propagation kind of comes from composition. And what is the composition here? I mean, just to kind of get an idea of what's going on. We won't go into all the details, but just to give you an idea how this works. So basically you can say, as these neurons are connected to each other, and basically you have, like, as I told you, you have here the sum of the inputs with the weights, and you have here this transmission function, which is called the action potential, and which then kind of puts out the outputs for the next layer, okay? And then here, of course, the outputs become the input of this layer, which then, again, using this action potential gives an output for the next layer, okay? Simple as that, but of course, back propagation. So from composition, what is the composition here? So the end value that I get here is kind of course, a composition of the previous layers. Yeah. So it's basically so basically, you can say what the output that I get is basically this function inside this function, inside this function, inside this function. Yeah. So each layer basically corresponds. Each layer, the more you get to the inputs, corresponds to some kind of function which gives the basically the input vectors for the next layer. Okay. What does this look like? So just to imagine this, we can write this a bit like this. So let's say we have an n layer network. Then we can say, okay, we have this kind of little g functions, if we want to call it like this, applied on the weights of the previous layer, okay, which gives you the final output. And in order of this, you basically have then always the functions from the previous layers until you get back to the front, okay? Is this kind of clear? If you look at it like this, we can say, okay, we have this here is Gn, this here is then the G before, and in order to get the values, the outputs here, well, basically I have a composition of this, the outputs of this layer times the outputs of this layer, okay? So I have this kind of composition, and what do you do when you derive these compositions? Well, basically you get the product rule, no? It's kind of inner derivative times outer derivative times outer derivative times outer derivative times outer derivative, no? And this is what is called back propagation, because I can take basically the derivative of this part here and then multiply it with the derivative of this part and multiply it with the derivative of this part in order to back propagate basically my weights, adapt my weights, and back propagate the errors, as it's called, okay? From this comes this back propagation algorithm, okay? So fine, so good. And of course, we can then calculate the loss function kind of in this way, and take this basically and calculate this gradient as we have it up here, in order to get it to update our weights in this back propagating manner. Okay, so fine, so good. This is how you train standard neural networks. So what does this mean? You show it basically an image of a cat. Okay, you get here out, okay, half cat, half dog, because it doesn't know. The real error would be one cat. I don't know what I said that I've shown it, but whatever, one cat, zero dog if it's a cat, yeah. And then basically we have an error, so we subtract this from the real output, from the outcome that came out, so 1/2. And there are several very interesting functions in order to do this. So some of these functions are, for instance, called categorical cross entropy. A categorical cross entropy function, you can look it up on the web in order to estimate this error. But this error basically is, of course, dependent on the weights, and then we adapt the weights using this back propagation algorithm so that basically we get the right outcome, or at least in the right direction. So you kind of can do just one gradient descent per image that you show it, or several gradient descents for an image. This is up to how one programs this story here. But in basically that's how it works, and that's how then you adapt the weights of the neural network in order to get the correct weights and a trained neural network, in order to have a trained classifier, basically. Okay. This is the classical neural network. Okay. Then different architectures exist, and one of the big architectures which kind of revolutionized, which brought a revolution into computer vision, were convolutional neural networks. Okay, so convolutional neural networks work different than this classical, which we call today dense neural networks. Convolutional neural networks use something which is, of course, as the name says, convolution, and they are a key, or they were key basically in order to get neural networks which are highly efficient in image classification. Okay, so these were the first neural networks that basically were able to distinguish for instance, characters, by showing characters to a neural network to say, okay, this is a A, this is a B, this is a 1 or a 2, or something like this. And supposedly, basically, they mimic somehow the visual cortex. So today, we know, I guess I've shown it to you in one of the previous slides, there was this cat experiment. So basically, these convolutional neural networks work like what these people basically in this cat experiment have seen, that in the visual cortex, basically mammals, they have this kind of convolution going on in order to detect, to better interpret images in their brain. Yeah. Okay. So fine, so good. What is convolution? So convolution, if you have a signal, basically, so this can be your inputs if you want to. If you have a signal, you have this kind of kernel, and what you do, you take the inner product between the kernel at a certain position with the signal, and then you get some kind of output at that point, and this is kind of the convolution, just that you have to slide the kernel. So I go to the next position, I take the inner product with the corresponding objects at the next position, so with this subvector here in the next position, so in this case it would be, what do we have here, 3 minus half minus 2, and then we kind of get here then we get here, as we can see, 0.5. Yeah, okay, so 3 minus 1 minus 2.5 yields 0.5. Easy to calculate, and you can then basically slide this over and get kind of this convolution out here. Yeah, so this is everything behind it. Very easy to understand. You have some kind of signal that looks like this. You have your kernel. Your kernel can of course be bigger or smaller. That's the way how this convolution works. And basically, using this convolution, you can do all kinds of nice things. If you have basically signals like this, you can do very nice things. For instance, you can take the derivative of the signal. You can imagine this. So if basically this is the signal at x and this is the signal at x plus delta h, yeah, to get to the derivative somewhere like this, you can say, okay, I get an approximation of the derivative if I take this here. If I put here 1, minus 1, 1, and 0 in the middle, and then you can imagine that, well, if these are the same, then you get 0, and if these are not the same, then you get the derivative of the signal. Okay? It's as easy as that. Okay? So fine, so good. And we have the same thing, of course, then in 2D. So we have here, you see, basically we have a 2D kernel, so a little 2D matrix, and we have here, for instance, the input, okay, and then we basically sum up this here with this here, and here the kernel is very simple because it's just 4 minus 4, it could have been way more complex, and we see in this case, well, 0 times 4 is 0, all the other elements are 0, so we don't have to calculate much, and 2 times minus 4 is minus 8, and we get in the middle of this object minus 8. And then, of course, we slide this little matrix, so this kernel, as we call it, and as we slide it over the points, we get the new points out in this convolution, which is the convolution image, if you want to. Okay? So things that you can do with this, so for instance, if I have this kind of 2D kernels, they correspond more or less to a derivative. You can think about it. And then basically you get this here. Here you get kind of vertical edges out, and here you get horizontal edges out. So let's imagine if I have these two kernels, and I'm in a flat region where basically the intensity is the same, or basically in an image I have exactly the same colors, if you like to. And there is no gray variance or anything, so it's just a flat image, then I basically get 0 out of this. But if the image is not flat, as for instance with this eye here, then I can apply this, and everywhere where there are changes, basically I get, of course, a signal out, and then I get a convolution, and the convolution then basically looks like this. What I get below here, this is then kind of the convolution of this image here above, and this is in image detection speak, we call this here the Sobel edge detector. So this applying this on this image gives you these edges out here. Yeah, okay. Nice to know, but what does this all have to do with neural networks? Okay, so neural networks, we have introduced them a bit above. What does this convolutional story has to do with neural networks? So you can do something like this. So you can say, okay, I have here my neural network just with the neurons, just as we have discussed them above. But on front of them, and of course this doesn't to be one layer, so in practice you can have one image here, and you can have several kernels which give you several convolutions out that you then can mix together in different ways. And you can have this in multiple stages, so you can say, okay, I have my input image, I have one convolution going on, then on this convolution I apply another convolution in order to get another convolution out, and I can do this not with just one kernel, but I can do this with multiple kernels, and get then, of course, not one image out, but if I have here 5 kernels, I get 5 images out that I can then feed, for instance, into a different neural network, into a standard neural network, and can classify here, for instance, in this classification here we have between a cat and a red panda, if this is a cat or a red panda, depending on the input image that I've shown it to it. Yeah, of course, then this would have to be two-dimensional, and the kernel would have to be two-dimensional as we have shown it above. Yeah, but and the idea basically is that, again, using this kind of backpropagation algorithm, of course, you can basically say, okay, just as you train here the weights, okay, I train the kernel. So I modify my coefficients in the kernel in a way so that I get basically the right image out. Yeah. So I take these kernel parameters into my list of parameters that are modifiable in this steepest descent. If you want to, of course, in practice you do this also with this backpropagation, because this is, of course, a composition here. Again, so you basically what happens here is determined by this convolution, and then it's determined by what happens here in these neurons. So you can then backpropagate this again to this composition law, yeah? So to the product rule, yeah? And say, okay, I change the values that I put here in the kernel in order to detect specific features, more or less. So you can see it like this, which make a cat distinguishable from a red panda. Okay. That's the basic idea behind it. I hope it's not too complex. I hope that everybody kind of got it how it works. And of course, in the real world, it looks a bit like this. So, for instance, you have here this kind of input image. On this input image, you, in this case here, they apply 1, 2, 3, 4, 5 convolutions. So they have 5 different filters, if you want to, 5 different little matrices, which generate these 5 new images, okay, to a convolution filter that they apply on this one here. And then they say, okay, they do what they call pooling. So pooling is nothing else than basically taking a little square here and calculating, for instance, the mean of the square and say, okay, the new pixel is the mean of the square. This is mean pooling, and then there exists also max pooling. So max pooling would be, okay, I take the maximum value of this little square and put it here. Okay, the different ways how to do it, but basically it's just subsampling of these images if you want to, yeah. And then they apply new convolutions on these images, get a new stack of images out here. They call this here a second stage, so basically they put some images to the side that they put then directly into this fully connected neural network. Here they again do convolutions in order to have very little images at the end, which they put into this classical neural network here. This is called classical neural network, is basically what they call here fully connected. And then basically they get the output here where they say 10, so they have 10 different classes on what these images are. Yeah? So I don't know what they were really treating with this image, but you can say, okay, is this an airplane, is this a car, is this a bicycle, something like this, and then basically the output gives them, okay, that's the right output. Okay, that's basically it. So this is how these neural networks work, and of course you can build all kinds of different architectures in the hope that basically by training them, so by adapting here basically the filters during the training and adapting here the weights in this classical neural network in order to get the right output. Okay, so different architectures exist. Here, everything that you have seen above is basically the feed-forward network. We will also quickly discuss so that you see, okay, you can't only do classification, but you can do all kinds of things with these neural networks. We will talk a bit about the autoencoder. In this little introductional course, we will not talk about recurrent neural networks, we don't have the time, and about more complicated architectures like the transformers or things like these. Which we leave to more advanced courses, basically. But let's quickly go to the autoencoder. So, what is it? So basically, we have here basically the input and the output, and we can basically say, okay, we show the same input to the output. Okay. Basically I can say here, okay, I show, for instance, here an image, and here I want to have the same image, okay? And then I train my neural network, very classical with this back propagation story, just that the input and the output is the same. But as you see, I kind of I have way fewer nodes here than I have at the input and then I have at the output, okay? And this allows me basically for dimensionality reduction, because what can I do with this? I can train the whole neural network and then I can kind of decouple it. So I can basically take, if I do this with images here, I get here one way to reconstruct the image, and here I get kind of to encode the image, and I can build a compression algorithm out of this, for instance, okay? Because I just basically take what I get out here and sum this up, and basically have what's inside these two nodes, and I can store this, yeah, from these 6 nodes here in this case, yeah. So here I just have a compression of 1/3, but with images this can be very high actually, for instance, and then I can say, okay, from these 2 values I want to reconstruct my whole data. I get back to the 6. And in many cases something like this works. Yeah. What I've written here also is this works in order to find new coordinate systems. So for instance, if I show here an image and here an output image, I kind of get this latent space here. This doesn't be an image, but if this here is some kind of high dimensional data, and this is some kind of high dimensional data, of course, too, because the input and the output is the same. But I can represent this basically in a low dimensional space, which gives me a new coordinate system, which is more efficient. It's kind of like doing PCA, something like this, like a kind of dimensionality reduction algorithm here going on. Which can be very efficient if this is very well trained. Yeah. Okay. Just to give you a little idea of what else you can do. As I said, many different things exist. Today, for instance, if you heard about ChatGPT and others, they use the transformer architecture. It's also kind of a classification task, yeah. But of course, with a different architecture than the convolutional neural network or than the classical neural network. Okay. Also, I told you about recurrent neural networks and other things, which we can't go over in this course, just that you have an idea that different things exist, but that these are the classical neural networks, and this should be a little introduction into this field of deep learning. We will then have a practical where we use these classical, where we basically use these convolutional neural networks in order to perform classification, and where we also will build an autoencoder in order to perform image compression. Okay, thank you so much. Bye bye. Have a great day.